Hi everyone, so just to recap what we were working on in previous class is we were studying second order differential equations. So we have second order derivatives in our differential equation, linear with constant coefficients. So in front of each of the dependent variable derivatives, we have a constant and it's homogeneous so that on the right side of the equation, we just have zero. So we were studying how we can solve differential equations of this form in the last class. And what we observed is that it makes sense that we might guess exponential functions as solutions to these differential equations. And then when we plug those solutions into the differential equation above, so when I substitute this into the differential equation up here, then we see that y equals e to the rt would be a solution as long as r is a solution to the corresponding characteristic equation for the differential equation. So here we just pull off the coefficients in front of the first, second, and zeroth derivative to give us the quadratic, linear, and constant terms in our quadratic equation. So let's consider the following example, I, that y double prime minus 7y prime plus 10y is equal to 0. So if we want to solve this differential equation, then the corresponding characteristic equation would be r squared minus 7r plus 10 is equal to 0. And this we can factor into r minus 5 times r minus 2 is equal to 0. So we have two roots to the characteristic equation. They are both real. That is 5 and 2. And so from this, we can see that e to the 5t would be a solution. E to the 2t would be a solution. Any constant times either one of those we showed would be a solution. And therefore, the sum of those two solutions gives us the most general solution to the differential equation. So this differential equation would have a general solution of c1 e to the 5t plus c2 e to the 2t. So these were the types of problems and the techniques that we went through in class last time. So let's take a look at a different differential equation. We talked about these as well. In particular, if we pull this over to the right side, then we saw that things such as y is equal to cosine of 4t, y is equal to the sine of 4t, that these made sense guessing and checking that those are actually solutions to this differential equation. So let's try and match up how our guesses worked last time with this method of finding the characteristic equation. So what would happen in the second one, rather than reading this differential equation and coming up with nice guesses for what the solutions might look like if I just try and apply the same characteristic equation approach. So now my characteristic equation would look like r squared. We don't have any first derivative term, so we have no linear term in our equation. And then we have a constant 16 is equal to 0. And so this does not have a real solution, right? There's no real number that when I square it and add it to the positive number 16, we're going to possibly get 0. But we do have r squared is equal to minus 16. So therefore, r equals plus or minus the square root of minus 16. Those would be the roots of this characteristic equation. And what we can see here, if I take the square root of minus 16, that actually gives me 4i. So I can see here that the roots of this characteristic equation are imaginary. These are complex. And what we'll work on in class is to see how these complex solutions lead us to sine and cosines as answers. So let's consider what we could do now with this differential equation, given that we found the roots of the characteristic equation, which happen to be complex here. So if we try the similar approach, which is, okay, We set up the characteristic equation. We figured out these are the roots of the characteristic equation. So therefore, let me come up with a guess for what the solution might look like. That would be a reasonable guess, just taking off of what we've been doing when we have real solutions. But now the question is, we've got these i's that are sitting in the powers. So how can we make sense of e being raised to an imaginary number? And how do we get sines and cosines out of that? Very strange. So to answer this question, what we're going to take a look at are what's called the Taylor series for a function. So this should have been something that you were introduced to in Calc 2. So let's just quickly review that. And then in class, we'll see how we can use Taylor series to generate real solutions out of these imaginary roots of the characteristic equation. So if we consider a function, let's say f of t, and we want to construct a Taylor series for this function around the point t equals a, then the definition of the Taylor series is given below. So it's an infinitely long series. It's a polynomial. We just have a bunch of powers of the variable t here in this case. So the real benefit of Taylor series is it allows us to approximate any function, even exponentials and trig functions, using polynomials. So when I simplify this, I get a polynomial. And so polynomials tend to be easier to work with computationally than some of these other functions. So being able to approximate these functions with polynomials is a really nice property. So let's review one of them, and then you'll have to do some work on the reading quiz for class relating to Taylor series. So let's consider the following function, f of t equals e to the 4t. And this is relating to the previous example. I am ignoring the I for the time being, but we'll consider that in class together. So if I want to find a Taylor series about t equals 0 for this function, f of t is equal to e to the t, well then let's use this formula over here. So now my value for a is 0. So we're doing this about 0. So we're going to have f of 0 plus f prime of 0, t minus 0 plus f double prime of 0 all over 2 factorial times t minus 0 squared and so on. So our a value is 0. So that means what I need to do in order to figure out each of the coefficients in this Taylor series is I need to calculate the derivative of this function and evaluate it at 0. So first of all, the first term, right, that is going to come from evaluating the function at 0. So we have that f of t is e to the 4t, so therefore f of 0 is equal to 1. And so let's start to complete this Taylor series then. So we have that e to the 4t is equal to f of 0 we now just found is 1. And then next, we're going to add f prime of 0 times t minus 0. So first, we would take the derivative of f, and then we would evaluate it at 0. So that gives us a value of 4. So then my next term in this Taylor series is going to be 4 times t minus 0. So that gave us this term over here. We found that f prime of 0 was 4, and then t minus 0, that's just t. And then we continue. So then we find the second derivative, and then evaluate that at 0. So again, each time we take the derivative, another power of 4 comes down. So now we would have a derivative, which is 16. And this is what goes right in the slot over here. So we have the second derivative at 0 is 16. We divide that by 2 factorial, which happens to be 2 times 1. So we divide that by 2. And then we multiply that by t minus 0 squared. So I'll just leave that there for now. And then we can simplify this. And then we continue on and go to the next derivative, the third derivative, which gives us 64. And so now this term over here, I have a 64 over 3 factorial. All times t minus 0 cubed. And then we can go on from there. And so if we simplify this quite a bit, or a little bit, then we can write this as 1 plus 4t, 16 over 2. Let's just write that as 8. T minus 0 is squared, is just t squared. And then we have 64 divided by 6. And simplifying that, that could be reduced to, for example, 32 over 3 times t cubed, and then dot, dot, dot. And we can actually even identify what the most general term would look like, because we've got a nice pattern in this derivative, and that is when I evaluate the nth derivative of f at 0, we are just going to get 4 to the nth power. So the general nth term, therefore, we have plus 4 to the n over n factorial times t to the n, and so on. So now we've taken this exponential, this one right here, and now we're able to write it as a polynomial, right? So now we just have a bunch of powers of t, and this is a great estimate approximation. If we take this out forever, this is exactly equal to the function e to the 4t for values of t that are close to 0. So here would be the simplified Taylor series for e to the 4t. So give this some practice, and we'll see how we can apply this in class to generate solutions to differential equations when the roots of the characteristic equation are complex. Okay, see you in class.